So as we introduce the whole concept of calculus, we want to start by looking at the concept of the limit. And I want to draw a picture for you here because I believe this picture will kind of show you the importance of what we're studying, okay? Calculus you can kind of view as like a house, okay? And we're going to go kind of Greco-Roman in our style of house here, okay? So here's calculus, here's the roof. Okay? The foundation of all of calculus is the limit. Okay? So here we have the foundation down here, and we're dealing with limits. Now, some people say that there are like 3 pillars of calculus. I prefer to view one of what they say is a pillar as the foundation because, as we will see, from the limit, we derive the 2 key pillars of calculus. All right? One being the derivative, and one being the integral. The great thing about calculus is that while it is a very challenging topic, there's only 2 things we ever really do in calculus. We take derivatives, or we find the integral. If one doesn't work, try the other. And especially the first couple of sections before we learn integration, there's really only one thing that we're going to be doing on every problem, and that is finding the derivative. Okay? Now, how we do that and how we apply it varies in numerous ways. Okay? But that's one thing that kind of makes calculus easy in a sense, is that there's really only 2 things that we're going to be doing the whole time. Okay? Now, what I'm going to be looking at with you here on limits today is an introduction and gives that foundation for what we're going to be starting tomorrow, which is derivatives. And you're like, wait, we're going through all of limits today. Yes and no. We're going through all the concepts of limits that you're going to need to know to be able to understand what we're doing. If you took Calc Honors, or if you took AP Calculus, we would delve way deeper into this. Okay? But we're going to hit it on a surface level so you guys understand the concept that we're dealing with and then are able to quickly make the jump over to derivatives. Our study of calculus in MathSL is very much a practical approach. We're not going to be learning Riemann sums, those of you who already had Calc Honors. We will see the definition of a derivative using the limit, but we're not really ever asked to use that, even though for some reason it's on your formula booklet. They haven't had a problem like that in over 10 years. I think maybe more like 15 years. The emphasis, though, in SL is, do you understand the concepts and can you use them more than all the nuts and bolts of the mechanics behind it, okay? So, but let's talk about what a limit is, okay? A limit is a value that the function approaches as x approaches a certain value, okay? And there, the key word is approaches. Now, sometimes it actually approaches and hits the value. For example, notice here, f of x is x squared plus 3. So I have it graphed here. Okay? What is the limit as x approaches 2? Okay? This is how I would read this. The limit as x approaches 2 of x squared plus 3 equals what? Okay? In this case, you can see here on the graph is continuous, all right? When the graph is continuous and we're trying to find the limit, you can just plug the number in and that's your limit, okay? It's very simple, all right? But I wanted to show you on this one here what happens with the table. Notice as I approach 2 from the left, or x values that are smaller than 2, it goes to 6.76, 6.84, 6.92. If I did a 1.99 or a 1.99999, it would be 6.999 and so on, getting closer and closer to this value of 7. Okay? as I come from the right-hand side, or values that are bigger than 2, you'll notice that I'm approaching 7 as well, just from above in this case. Okay, so 7.2, 7.1, 7.08. If I had 2.01, it would be 7.00 something. Okay, and you would just get more and more zeros. If I put like a 2.00001, I'd have 7.000 something. Okay, getting closer and closer to 7. All right, like I said though, because this is continuous, I can simply plug in the value 2, and I get 2 squared is 4 plus 3 is 7. Okay? So I would say that the limit as x approaches 2 of x squared plus 3 equals 7. Okay? Now, I said that the limit is the value that the function is approaching from both sides. Okay? It's approaching this from both sides. Here we have this piecewise function, and we have what's called the left-hand limit and the right-hand limit. Okay? Notice the notation here. If I have the left-hand limit, I have this little negative sign after whatever the value is that x is approaching. So this is saying the limit as x approaches c from the left of f of x. Okay? And if I put a little plus sign after the c, I have the limit as x approaches c from the right of f of x. Okay? Yes?
Are left and right hand limits limited to only piecewise functions, or can they function in?
No, any function.
Okay.
Yeah. And that's something we would examine a lot more closely in a pure calculus class. In order for a limit to actually exist, the left and right sides have to approach the same value. Okay? So for example, you'll notice here, I have a piecewise function and the junction here is at x equals 2, where these connect. And you'll notice the limit as we approach 2 from the left is 0, because as we're along this parabola, we are approaching the value 0. Okay? As we approach 2 from the right, this little plus sign, I'm on the line and I'm approaching 2 from the right, and it's also approaching the value of 0. Okay? Because these are the same number, I can say the limit as x approaches 2 equals 0. Okay? Well, that's the thing. It may not always be that way. So let's say that instead of this line here, let's say I had this like open point and the line was going like this. Okay? It's not continuous, but that doesn't necessarily mean that the limit will not exist. What that means is that I need to look at what it's approaching. In this case, as we approach from the right, it's not approaching 0, it's approaching 3. Okay? Now, since the left and the right-hand sides are not approaching the same value, we would say that the limit does not exist. Okay? Because the limit has to be a specific number that we are approaching from both sides of the x value that we're looking at. Okay? Now, could we find the limit as x approaches 0? Sure, it's actually -4. Could we find the limit as x approaches 7? Yeah, it'd be way over here on the line. But the limit as x approaches this specific value of 2 would not exist. Okay? So, we do have cases like that. Again, we aren't doing a ton with limits, but I want you to understand this concept here before we get to derivatives. Okay? So here's what we were just talking about. Does a limit exist as x approaches a value? We just saw one with a piecewise function. We could also have a function like this, the radical function, as x is approaching 0? Well, you know, because you all know your parent functions, you know that 0, 0 is an endpoint of this radical x function. Okay? Well, I can approach 0 from the right, and as I approach 0 from the right, my function is approaching the value of 0. Okay? The y-coordinate is getting closer and closer to 0. Okay? So that's what you can see right here. The limit as x approaches 0 from the right of radical x equals 0. Okay? However, there is no function to the left of that. So we would say the limit as x approaches 0 from the left does not exist. Therefore, the limit as x approaches 0 does not exist. Okay? Now that's just at that value of 0. If I had x approaching 0.0001, we could find that limit. Okay?
Why is it DNA?
Because you have an endpoint here, there is no left-hand limit. So the left-hand limit and the right-hand limit are not equal. Okay, they have to both exist and they have to be equal to each other. Okay? Does that make sense? Yeah. All right. So, building on what we did in the last one, okay? Or in our first example, I mentioned that because that parabola was continuous, we could simply plug in the values. So the question is kind of naturally, all right, when are we allowed to just plug it in? As long as the function is continuous around the value of x, or we could just say at x, and it's defined on either side, unlike the radical x. Then we can find the limit by evaluating the function there. Okay, so let's say f of x is x squared plus 3x plus 2 over 13x plus 8. Alright, now the domain here is x cannot be negative 8/13, because that would make our denominator 0. This would be the graph of this thing. Okay, but let's say I was taking the limit as x approached 4. Is this continuous around 4? Yeah. So guess what? I can simply plug in 4, 16 plus 12 plus 2 over 52 plus 8, and I get a half. So the limit as x approaches 4 of this would just be a half. Okay? However, if I tried to take the limit as x approached negative 8/13, I see that there's an asymptote there. See where the stuff you learned in pre-calc honors about rational functions is going to come into play here? Okay? So we have an asymptote at x equals negative 8/13. So guess what? The limit as x approaches that, you'll notice it's going to infinity or negative infinity on the two sides. Okay? Now, even if these were both going up to positive infinity or both to negative infinity, we would still say the limit does not exist because infinity isn't a number. Okay? And if the limit is going to infinity, we would not say it equals infinity because it's not a number. So we say the limit does not exist, or we can make the comment that it's going towards infinity. However, in this case, one is going down to negative infinity, the right-hand limit's going up to positive infinity, so we would say the limit does not exist. They're not approaching the same value on either side of that number. Okay? Now, how could I have a discontinuity here and still have a limit exist then? Can you think of it? A discontinuity is a place where the function's not continuous, like here at the asymptote. What's the other kind of discontinuity? A hole. Alright? Guess what? If I were to modify this original function, and I made it x minus 4, I multiplied it by x minus 4 over x minus 4. Guess what? Over here at 4, there would be a hole. But that actually would not change the limit at all. Because the value of the function would be approaching a half, and approaching a half, even though it doesn't actually equal a half there, the key word is approaching. Okay? And the way we would handle that actually is we would reduce, this is called, a hole is also called a removable discontinuity, because if we have it factored out, we can cancel those out, and then I would evaluate it the same way I did the original one. Okay? So we could cancel out, remove the hole.
Wait,
Wouldn't it still be there?
Yeah, don't you have to keep the hole there, but if it has the same on the top and bottom, then that's how you know there is a hole? Makes sense.
Well, yes, that is how we know it's a hole, and we can remove it. We're going to remove it temporarily just so that we can evaluate like we did down here. Okay? So, if we were given this rational function, we would say, okay, as x is approaching 4, there's a hole. I'm going to cancel those out and then evaluate it to equal a half. And that'll tell me. It's just like actually when you were in pre-calculus studying rational functions, one of the features you guys had to find was the coordinates of the hole. So you identified where that happened, and then you needed to find the y coordinate of where that hole was. And you did it by factoring, canceling out, and then plugging in the x. Well, that's what we're doing here to find not a y coordinate of a hole, but the value of the limit.
So
Okay.
you're just taking it out of the equation.
Yeah.
You're not actually like taking the hole away.
No, the hole is still there in the original function. We remove it so that we can figure out what the coordinate would be, and then what the limit would be. Okay? Alright. Now, what I just showed you here, if I had plugged 4 into this original function with the x minus 4s, what would that come out to? 0 over 0. Okay? That's actually what's known as an indeterminate form. Indeterminate means unable to determine. Okay? When you have that, you have to deal with that in one of a variety of ways. One of those ways is to factor and reduce like this. If it has radicals, we can actually rationalize, okay, and get rid of them that way. If it's a complex fraction, we can multiply by the denominators in order to get rid of the complex part of that fraction, and then see what happens. And then there's another rule that you'd learn in AP Calc called L'Hopital's rule, where you'll actually take the derivative of the top and bottom and then take the limit, okay? But we're not going to do that, okay? All of that is kind of beyond where we need to go for this course, all right? But I wanted to throw it out there to you because there's a lot that you can do with limits, okay? So let me just finally address a couple of properties here. And this will actually help us because most of these properties carry directly over to finding derivatives, okay? The limit of a polynomial. What's the domain of a polynomial? Any polynomial. The domain of a polynomial.
1.
A line, oh come on. A line, a quadratic, a cubic, a quartic, all those have the same domain. What's the domain here?
0.
So x equals 0 is the only possible value that will work in any...
Oh, all real numbers.
Yes, thank you.
Oh.
Come on guys, you need to know what domain is. Alright, domain is what x can be. X can be anything, for any polynomial. So guess what? Since any polynomial is continuous at all real numbers, it doesn't matter what x is approaching, you can find the limit by evaluating. Okay? That's why partly too you guys needed to learn the domains of your parent functions.
Why is infinity the wrong answer?
Infinity is a concept, it's not a number. So we would not say that the limit equals infinity.
But when we use sign of infinity, we are writing the answer for domain or the last year.
Oh, for a domain, well, you wouldn't just say the domain is infinity. You would give an interval, negative infinity to positive infinity, like that. Okay? You would put something like that. You wouldn't just say, oh, the domain is infinity. Okay?
So I can still use infinity. I just need to say from negative infinity to positive.
Yeah. Okay? So that's one thing. A constant. Guys, a constant function doesn't change value. Right? That's why it's called a constant function. Okay? So a constant function, if I'm taking the limit, no matter what I approach, the constant function is always going to equal the same thing. So if I have the constant f of x equals b, then the limit as x approaches anything of b is just going to be b. Okay? So if I have the line y equals 5, it doesn't matter if x is approaching 0 or negative 100 or 3,000, it's always going to equal 5, so the limit equals 5. Okay? Then we have this other, and this one is going to be really, really useful when we get to derivatives in particular, and that is the constant multiple. If I'm taking the limit of a function times a constant, I can take the limit of the function by itself and then multiply that limit by the constant. Okay? That we're going to use with derivatives. When we learn a rule and we know how to find the derivative of a particular function, if we have 5 times that function, we can still just take the derivative of the function and then multiply that by 5. Okay? So that's a rule that carries directly over. Okay? Then we have a sum, a product, the limit of a rational function, and the limit of a power. All of these work very similarly. Here's what we just saw with the constant multiple. But the limit of a sum, if I have two functions added together, like the limit of sine of x minus radical x. Those are two different functions. I can just take the limit of sine of x and then the limit of radical x and then add those limits or subtract those limits. Okay? We can break them down. I can do the same thing if it's multiplication. If I have radical x times sine of x, I could take those two limits first separately and then multiply those together. I can also do it with division as long as the denominator doesn't equal 0. Okay? As long as I'm approaching something that would still be in the domain, I can just take the limit of the numerator, take the limit of the denominator, and divide them. Okay? And then finally with the power. If I have a function raised to a power, like let's say I have, the quadratic x squared plus 3x, and that whole thing is raised to the 8th power, I don't have to use the binomial expansion to expand that whole thing out and then plug in. I can just take the limit of the quadratic, get that number, and raise that number to the 8th power. Okay? So, again, a couple of quick little rules with limits that we can look at. So I want to close drawing this whole idea down to the concept of the derivative. Okay? I know we've looked at a real whirlwind tour of limits. Okay? But the whole point of that was to bring us to this point. Okay?
Is derivative just like the chain rule and stuff like that?
We have the chain rule. We have a lot of different rules that we're going to be using. Okay?
Well, that's what it is, right?
So I want to talk about what we're actually trying to find and what the problem is here. Calculus was invented by two different mathematicians. And basically the two pillars were derived, one by Sir Isaac Newton and one by Sir Gottfried Wilhelm von Leibniz. Okay? All right? They both derived these in trying to solve different problems. One of the problems was the concept of optics. People were exploring space and they were trying to develop microscopes, so lenses and magnification and that sort of thing, bending light was a major thing. And how do we actually bend light intentionally rather than just kind of, hey, let's make a lens and see what it does? Okay? The whole problem with that, though, is that in order to create a lens that bends light exactly the way you want it to, you have to know what angle it is. Well, a lens is curved. So you can't really measure an angle. But if I have this point that I'm working with, and I want the angle at that point, okay, you guys know the basic angle of reflection equals the angle of incidence. In other words, if I were to reflect something off of this point, the angle of incidence is the angle away from what we call the normal, which is perpendicular to the surface. That's the angle of incidence. And this thing is going to reflect off at exactly the same angle. This is how we get to predict what our lens is actually going to do. Okay? Now, the problem with this is when we're dealing with a curve, we can't just measure the angle. So what we had to do is we had to figure out what angle the surface was at that moment. So right at this point, what angle are we at? That's what the derivative gives. And then from there, we're able to find the normal and then find the angle. Okay? That's the problem that they were trying to solve. So, backing up here a little bit, the basic concept of the derivative is that the derivative is the slope, or if you remember back when you learned about slope, slope is all about rate of change. Okay? The derivative is the slope or rate of change of the tangent line at a given point. Okay? So we just mentioned this tangent line here because we want to be able to figure out some angles related to it. And remember, a tangent line intersects the function at only one point. Okay, so it just, when you're looking at it, it just barely touches the function. It only hits it once. It doesn't go through two different points. Okay? Now, this poses a problem because in order to find slope, you got to have 2 points. Okay? You find the slope between 2 points and use your slope formula and you've got it. Okay? But what we will do here, and this is one thing we're going to develop, is we actually use what's called a secant line. Okay, let me get a different color here. Okay, so if I wanted the slope of this tangent line, like we just said, to find slope we need 2 different points. Okay? So, for example, I could find the slope of this. Now, this line here that hits it in 2 points is called a secant line. All right, and obviously, if I found the slope of that line, that's not going to be close at all to the slope of the tangent line. Okay? But what I can do is I can actually move this point closer. And guess what? If I found the slope between those 2 points, that would be a little bit closer to what the slope of the tangent line is. Okay? How could I get an even better?
Move it closer?
Yeah, okay. Move it closer. So if I moved it here, I'd get an even better approximation. If I moved it right here, I'd get an even better approximation. So thinking about what we were doing, this is a limit, okay? This is a limit. And it's a limit, if you think about it, we have rise over run. We look at that run, we'll use delta x. Okay? Well, here we have another rise over run. And here we have another rise over run. What's happening to the run as the point gets closer and closer and closer? It gets smaller and smaller and smaller. Okay? So put that in terms of a limit. It's the limit as the delta x approaches 0. Okay? So what we're doing in order to find that slope, okay, the slope at the point is the limit as delta x approaches 0 of the slope of the secant line. Okay? Slope of the secant line. Now you don't need to write that down right there, but because we have a better form of this. Now the slope of a secant line we're going to generalize here, okay? So here's our point xy, right? Mm-hmm. This point right here is going to be x plus delta x, okay? Mm-hmm. And the y-coordinate of this is going to be f of x plus delta x, okay? Mm-hmm. Now if I'm doing slope, all right, my slope, limit as delta x approaches 0, well, my y-coordinates are f of x plus delta x and f of x, okay, because this point xy, the y is f of x, right? Well, the change in the run, the change in the x, is x plus delta x minus x. Well, x plus delta x minus an x ends up just being delta x, because the x and the minus x cancel out. And guess what? That right there is the definition of the derivative. Okay? There we have it right there. We can use delta x, or in this case we have it written down as h. Alright? It doesn't matter what variable you use to represent your run, it's the same idea. Okay? So let's take a look at some terms, and then in our next lesson we're going to actually learn the some rules for this. Okay? So differentiation, that's a term you need to know. Differentiation is just the act of finding the derivative of a function. Okay? It's a big term, just means you're finding the derivative. If something is differentiable, that means we are able to differentiate it. Okay? So we are able to take the derivative. There are certain cases where you can't take the derivative. For example, at an asymptote, or any kind of discontinuity. If the function's not continuous, you cannot take the derivative. So it's not differentiable. Another instance where we cannot take the derivative is if there is a sharp change of direction. In other words, the curve is not smooth. So for example, if we had some kind of a piecewise function where we had a curve like this and a line like this, at this point right here, it would not be differentiable. Okay? It might be more drastic, like an absolute value function like this. At that vertex point there, it's not differentiable. Okay? And like I said, any kind of a discontinuity, like a hole or an asymptote, it's not differentiable. Okay? And then we have some notation. There's two types of notation for a derivative. One is the differential notation, which is dy dx. Okay, dy over dx. You kind of write it as a fraction. If you think about it, that's slope, right? D instead of delta, change in y over change in x. Okay, that's where that comes from. Also, we have the prime notation. F prime of x we read as the derivative of f. Okay? So that's the groundwork. The nice thing for you is that SL really does not require you to use this limit definition. Okay? This is for people who have never had any calculus before. I call that kind of the dirty trick of calculus class. Because in college calculus, you'll spend about a week or so doing derivatives using that limit definition. In AP calculus, we do it for a couple of days. And then, after doing all those problems that take anywhere from half a page to a couple of pages each, then you learn the rules, and you find out, wait, I could have just written down the answer. And that's what we're going to skip to in our next lesson.